Hello and welcome to Applied Statistics in Python for Machine Learning Engineers. I'm Mike West and I'll be your instructor for this class. The field of statistics is hundreds of years old, and statistical methods are central to working through predictive modeling problems with machine learning. Statistical methods refer to a range of techniques from simple summary statistics intended to help you better understand your data, to statistical hypotheses tests and estimation statistics that can be used to interpret the results of experiments and predictions from your models. I've designed this course to teach you a step-by-step basis for statistical methods with concrete and executable examples in Python. This isn't solely a theory-centric course. In the course, you're going to use Python to aid in your learning of applied statistics for real-world applications. In the course, you'll learn how to calculate and interpret common summary statistics and how to present the data using standard data visualization techniques. You'll learn about mathematical statistics that underlie much of the field, such as central limit theory and the law of large numbers, and why these are so important in understanding machine learning. You'll learn how to evaluate and interpret the relationship between variables and the independence of the variables. You'll learn how to calculate and interpret interval statistics for distributions, population parameters, and observations. In the course, you'll learn how to use statistical resampling to make good economic use of available data in order to evaluate predictive models. Statistics is a collection of tools that can help you get the answers to the important questions about your data. You can use descriptive statistical methods to transform raw observations into information that you can understand and share. You can use inferential statistical methods to reason from small samples of data to whole domains. In this course, you're going to learn why statistics is so important in machine learning and the types of methods that are available. Machine learning and statistics are two tightly integrated fields. So much so that statisticians refer to machine learning as applied statistics or statistical learning rather than the computer science-centric name. Machine learning is often presented to new learners with the assumption that the learner has some background information in statistics. This course is not designed to teach you everything you need to know about the theories or techniques behind statistics. It was designed to give you an understanding of how statistics works in concert with machine learning. In the course, we're going to cover 6 core aspects of statistics for machine learning. Number 1. The first thing we're going to do is provide you with an introduction of the field of statistics, the relationships to machine learning, and the importance that statistical methods have when working through a predictive modeling problem. The second thing we're going to do is build a foundation of statistics specific to machine learning. I'll introduce you to descriptive statistics, data visualization, random numbers, and important findings in statistics such as the law of large numbers and the central limit theorem. Thirdly, we're going to cover hypothesis testing. These are statistical hypothesis tests for comparing populations of samples and the interpretation of tests with p-values and critical values. Fourthly, we're going to talk about resampling. We're going to cover methods from statistics used to economically use small samples of data to evaluate predictive models such as k-fold cross-validation and bootstrap. Number 5, we're going to talk about estimation statistics. This covers an alternative to hypothesis testing called estimation statistics, including tolerance intervals, confidence intervals, and prediction intervals. This last section is going to cover non-parametric, statistical hypothesis testing methods for use when the data does not meet the expectations of the parametric tests, i.e., it's not in your typical normal distribution. Almost every example throughout the course is going to have Python-related code to help cement the lecture topics. By the end of this course, you'll have a solid foundation on how to apply statistics to your machine learning models. Hello and welcome back. Let's discuss if this course is right for you. So the title of the course is Applied Statistics in Python for Machine Learning Engineers. So what does applied mean? Well, applied means real-world usage. Like this isn't going to be a theoretical course. I'm not going to show you the difference between descriptive and inferential statistics and then not anything else. Theory is important, but application of that theory is critical for a machine learning engineer. All right, so let's jump over here to a Jupyter Notebook. Let's take a look at some code. So let's import pandas. Let's go ahead and import scikit-learn and XGBoost. Let's go ahead and run these. Let's import some data. Let's go ahead and take a look at a few columns. Well, let's look at the head function. All right, so this is the Titanic data set. And you can see that value there is a nan. A nan in Python is not a number. That's a missing value in machine learning. Replacing missing values in machine learning is a statistical technique called immutation. I'm not going to tell you what immutation is and tell you, well, in statistics, immutation means replacing missing values. because that's great, but it doesn't mean anything if I don't show you what exactly replacing missing values does to your model. So is the course right for you? Are you a programmer? Programmers are notoriously great at programming and not so good in statistics. So if you're a programmer and you're thinking about making a move to machine learning, you're going to need to have solid statistics skills. You would be my target student. If you're new to programming, then you are also my target student. If you're moving from any field to machine learning, whether you're coming from college or whether you're making a lateral move inside of IT, whatever your path to machine learning, it's going to collide head-on with statistics. So if you're new to machine learning, you're going to have to know applied statistics. You're going to have to know the basics of statistics and being able to take your statistical knowledge and apply it to your data. So if you're new to machine learning and you want to be a machine learning engineer, then this course is for you. Statistics is a subfield of mathematics. It refers to a collection of methods for working with data and using that data to answer questions. Because the field is comprised of a disparate group of methods for working with data, it can be confusing to beginners. It can be hard to draw a line between methods that belong to statistics and methods that belong to other fields of study, like machine learning. Often a technique can be used both for classical methods of statistics and for modern algorithms used in feature selection or modeling. Statistics can be broken down into two large categories. The two large categories are descriptive statistics and inferential statistics. Descriptive statistics provides information that describes the data in some manner. For example, suppose a pet store sells cats, dogs, fish, and birds. If 100 pets were sold, and 40 out of the 100 were dogs, then one kind of description on the data of the pets that were sold are 40% dogs. The same pet shop may conduct a study of number of fish sold each day for a month and determine that an average of 10 fish were sold each day. That average is an example of descriptive statistics. Some other measurements in descriptive statistics answer questions such as, how widely is data dispersed? Are there a lot of different values? Are many of the values the same? What's the middle value in my data? Graphical representations of data is another part of descriptive statistics. Examples of visual representations are histograms, bar charts, pie graphs, to name a few. Almost everything I do on a daily basis is descriptive statistics. All right, the next large category is called inferential statistics. It's about using data from a sample and then making inferences about that larger population from which the sample was drawn. The main goal of inferential statistics is to draw conclusions from a sample and generalize them to a population. It determines the probability of the characteristics of a sample using probability theory. The most common approaches here are hypothesis tests and analysis of variances. For example, suppose we are interested in the exam marks of the students in the United States, but it's not feasible to measure the exam marks for all those students. So we take a sample of that population. The sample now represents the larger population of the students in the U.S. We would consider this sample for a statistical study for studying the population from which it came from. Statistics and machine learning are two closely related fields. In fact, the line between them can be a little fuzzy at times. Nevertheless, there are methods that clearly belong to the field of statistics that are not only useful, but invaluable when working on machine learning projects. One of the hardest parts of predictive modeling is the framing of the problem. This is the selection of the type of problem. Is it going to be a regression or a classification problem? And perhaps the structure and types of inputs and outputs of the problem. The framing of the problem is not always obvious. Statistical methods that can aid in the exploration of data during the framing of the problem include EDA, or exploratory data analysis, and data mining. EDA allows you to visualize your data to gain insights, and data mining is the discovering of relationships and patterns in your data. Data understanding means having an intimate grasp of both the distribution of the variables and the relationships between those variables. Some of this knowledge may come from domain expertise or require domain expertise in order to interpret it. Two large branches of statistical methods used in this understanding are summary statistics. These are methods that are used to summarize the distribution and relationships between the variables using statistical quantities. And secondly, data visualization. These are methods used to summarize the distribution and relationships between variables using visualization of charts, plots, and graphs. Observations from a domain are not always pristine. Although the data is digital, it may be subjected to processes that can damage the fidelity of the data, and in turn, any downstream processes or models that make use of that data. Some examples include corruptions, error, and data loss. The process of identifying and repairing issues within the data is called data cleansing. Statistical methods are used for data cleansing. Two examples are outlier detection and immutation. Methods for identifying observations that are far from the expected value in a distribution are called outlier detections. Methods for repairing and filling in corrupt or missing values in observations are called immutation approaches. Not all observations or variables may be relevant when modeling. The process of reducing the scope of the data to those elements that are most important for making predictions is often called data selection. One approach to data selection is data sampling. These are approaches that systematically create smaller representative samples from larger data sets. There's also feature selection. These are methods used to automatically identify those variables that are most relevant to the outcome of a variable. Data often can't be used directly for modeling. Oftentimes, transformations are required in order to change the shape or structure of the data to make it more suitable for the chosen framing of the problem or learning algorithm. Data preparation is performed using statistical methods. This includes methods such as standardization and normalization. Another group of examples are encoding methods, such as integer encoding and one-hot encoding. A crucial part of the predictive problem is evaluating a learning method. This often requires the estimation of the skill of the model when making predictions on data not seen during the training of the model. Generally, the planning of this process of training and evaluating a predictive model is called experimental design. This is a whole subfield of statistical methods. As part of implementing any design, methods are used to resample data in order to make economic use of the available data in order to estimate the skill of the model. A given machine learning model often has a suite of hyperparameters that allow the learning method to be tailored to a specific problem. The configuration of hyperparameters is often empirical in nature, rather than analytical, requiring large suites of experiments in order to evaluate the effect of different hyperparameter values on the skill of the model. The interpretation and comparison of the results between different hyperparameter configurations is made using one of the two subfields of statistics. The first of that is statistical hypothesis tests. These are methods that quantify the likelihood of observing the result given an assumption or expectation about the result. The second is estimation statistics. These approaches are methods that quantify the uncertainty of the result using confidence intervals. The process of selecting one method as a solution is called model selection. This often involves a suite of criteria from both the stakeholders of the project and a careful interpretation of the estimated skill of methods evaluated for the problem. Finally, it will come a time to start using the final model to make predictions on the new data, where you don't know the real outcome. As part of making predictions, it's important to quantify the confidence of the prediction. An example of this is called estimation statistics. These are approaches or methods that quantify the uncertainty for a prediction via prediction intervals. Many observations fit a common pattern or distribution called a normal distribution, or formally referred to as a Gaussian distribution. The terms normal distribution and Gaussian distribution are synonyms. In statistics, a lot is known about Gaussian distributions. Because a lot is known about this distribution, you often want your data to take this kind of distribution. The distribution of data refers to the shape it's in when you graph it. The most well-known distribution of continuous values is called a bell curve. It's known as a normal distribution because it's a distribution that a lot of the data falls into. Statistical data can be classified in several ways. The first characterization is whether the data is numerical or not. If your data is numerical, you have quantitative data. If your data is not numerical, you have qualitative data. Qualitative data is often referred to as categorical data. Within quantitative data, there are subtypes of data. The first type is discrete data. These are whole numbers that can't be divided. An example of discrete data is the number of people in a classroom. For example, you can't have 19.5 students in a classroom. The next subtype is continuous data. This is data that continues on forever. Well, at least that's how you can think about it. This kind of data can be broken down into smaller and smaller units. Next, let's tackle some data measurement scales. A measurement scale indicates the type of mathematical operations that can be performed on the data. Most commonly, measurement scales are used when describing the properties of variables. In statistics, there are 4 core measurement scales. They are nominal, ordinal, interval, and ratio. The simplest of the measurement scales is nominal. Nominal scales are used for labeling variables without any quantitative value. Nominal scales can simply be called labels. A good way to remember this is that nominal sounds like name, and nominal scales are like names or labels. For example, consider data showing the preferred colors of 5 people. blue, green, pink, and brown. The next scale is ordinal. With ordinal scales, the order of the value is what's important. However, the differences between each value is not really known. For example, is the difference between okay and unhappy the same as the difference between happy and very happy? Well, we can't say. The next scale is interval. Interval scales are numeric scales in which we know both the order and the exact differences between the values. The canonical example here of interval scales is the Celsius temperature, because the difference between each value is the same. For example, the difference between 30 and 50 degrees is a measurable 20 degrees, as is the difference between 90 and 70 degrees. Interval scales are nice because the realm of statistical analysis on the data sets opens. For example, central tendency can be measured by mode, median, or mean. Standard deviation can also be calculated. Our last scale is ratio. Ratio scales are the ultimate nirvana when it comes to data measurement scales because they tell us about the order and they tell us the exact value between units. Additionally, you also have absolute zero, which allows for a wide range of descriptive and inferential statistics to be applied. Good examples of ratio variables include height, weight, and duration. We can think about data being generated by some unknown process. The data we collect is called a sample, whereas all the possible data collected can be called a population. A data sample is a subset of all the observations from a group, while the data population is all the possible observations from that group. This is an important distinction because different statistical methods are used on samples versus populations, and in applied machine learning, we are often working with samples of data. If you read or use the word population when you're talking about data in machine learning, it very likely means sample when it comes to statistical methods. Two examples of data samples you'll encounter in machine learning include training and testing data sets and the performance scores for a model. When using statistical methods, we often want to make claims about the population using only observations in the sample. Two clear examples of this include the training sample must be representative of the population of observations so we can fit the useful model. Secondly, the test sample must be representative of the populations of observations so that we can develop an unbiased calculation of the model skill. Because we are always working with samples and making claims about a population, it means that there is always some uncertainty, and it's really important to understand and then report that uncertainty. A distribution of the data refers to the shape it's in when you graph it, such as a histogram. The most commonly seen and therefore well-known distribution of continuous values is a bell curve. It's also known as a normal distribution, because it's the distribution that a lot of data falls into. It's also known as the Gaussian distribution, more formally named for Carl Friedrich Gauss. Therefore, you'll see references to data being normally distributed, or Gaussian, which are interchangeable, both referring to the same thing, that the data looks Gaussian. Some examples of observations that fit a Gaussian distribution are the people's heights, IQ scores, and body temperatures. All right, let's jump over to some code and create a normal distribution. Running the examples generates a plot of the idealized Gaussian distribution. The x-axis are the observations, and the y-axis is the likelihood of each observation. In this case, observations are around 0, 0. Observations around the 0 mark are the most common observations, and observations around the -3 and the +3 are rare or unlikely. Before we dive into important summary statistics for data in Gaussian distributions, let's generate sample data that we can work with. We're going to use the rand function in NumPy to generate sample distributions of data drawn from a Gaussian distribution. There are two key parameters that define the Gaussian distribution here. They are the mean and the standard deviation. You'll delve deeper into these parameters later, as they are key statistics to estimate when we have data drawn from an unknown Gaussian distribution. The rand function will generate a specified number of random numbers drawn from a Gaussian distribution with a mean of 0 and a standard deviation of 1. We can then scale these numbers to a Gaussian distribution or by choosing a rescaling number. This can be made consistent by adding the desired mean, for example, the mean of 50, and multiplying that value by a standard deviation of 5. Running the example generates a dataset and plots a histogram. You can almost see the Gaussian shape to the data, but it's a little blocky. This highlights an important facet to distributions. Most of the time, the data is not going to look like a perfect Gaussian distribution, but it will have Gaussian distribution-like qualities. It's almost Gaussian, and maybe it would be more Gaussian if we plotted it a different way, scaled it in some way, or gathered more data. Often, when we're working with Gaussian-like data, we can treat it as Gaussian and then use all the same statistical tools and get reliable results. In the case of this dataset, you don't have enough data and the plot's blocky because the plotting function chooses an arbitrary size bucket for splitting up the data. You can choose a different, more granular way to split the data and better expose the underlying Gaussian distribution. Let's run the example and then bin our data into 100 splits. When we do this, we can clearly see it's a more Gaussian-like distribution. The dataset was generated from a perfect Gaussian, but the numbers were randomly chosen, and we only chose 10,000 observations for our sample. You can see, even with this controlled setup, there's obvious noise in the data. This highlights another important point, that we should always expect some noise or limitation in our data sample. The data sample is always going to contain errors compared to the pure underlying distribution. Hello and welcome back. Let's calculate some measures of central tendency in Python. Before we get started, let's import mean from NumPy. Next, the code calculates and prints the mean of the sample. The calculation of the arithmetic mean of the sample is an estimate of the parameters that underlie the Gaussian distribution of a population from which the sample was drawn. As an estimate, it's going to contain errors. Because we know the underlying distribution has a true mean of 50, we can see that the estimate from the sample of 10,000 observations is pretty close. The mean is easily influenced by outlier values, that is, rare values from the mean. These may be legitimate rare observations on the edge of the distribution of errors. Furthermore, the mean value can be misleading. In the case of outliers or a non-Gaussian distribution, an alternative and commonly used central tendency to calculate is the median. The median is calculated by sorting all the data and then locating the middle value in that sample. This is straightforward if there's an odd number of observations. If there are an even number of observations, the median is calculated as the average of the middle two observations. You can calculate the median of a sample by using the median function in NumPy. Running the example, you can see the median is calculated from the sample and printed. The result is similar to the mean because the sample has been drawn from a Gaussian distribution. If you had a different non-Gaussian distribution, the median may be very different from the mean, and perhaps a better reflection of central tendency to the underlying population. The variance of a distribution refers to how much on average the observations vary or differ from the mean value. It's useful to think of the variance as a measure of the spread of distribution. A low variance will have values grouped around the mean, narrow bell-shaped, whereas a high variance will have values spread out around the mean, wide bell-shaped. In the example on screen, you can plot the idealized Gaussian distribution with low and high variance. Running the example plots an idealized Gaussian distribution, the blue with the low variance grouped around the mean, and the orange with the higher variance with more spread. You can calculate the variance of a data sample in NumPy by using the var function. It's hard to interpret the variance because the units are squared units of the observation. You can return the units to the original units of the observations by taking the square root of the result. For example, the square root of 29,939 is about 4.9. Oftentimes, when the spread of a Gaussian distribution is summarized, it is described using the square root of the variance. This is called standard deviation. The standard deviation, along with the mean, are the two key parameters required to specify any Gaussian distribution. You can see that the value of 4.9 is very close to the value of 5 for the standard deviation, specified when the samples were created for the test problem. Measures of variance can be calculated for non-Gaussian distributions, but generally require that the distribution be identified so that a specialized measure of variance specific to that distribution can be calculated. Randomness is a big part of machine learning. Randomness is a tool or a feature in preparing data in the learning algorithms that map the input data to the output data in order to make predictions. In order to understand the need for statistical methods in machine learning, you need to understand the source of randomness in machine learning. The source of randomness in machine learning is a mathematical trick called a pseudo-random number generator. There are many sources of randomness in the applied machine learning space. Randomness is used as a tool to help learning algorithms to be more robust and ultimately result in better predictions and more accurate models. Let's check out a few sources of randomness. There is a random element to a sample of data you've collected from the domain that you'll use to train and evaluate the model. The data may have mistakes or errors. More deeply, the data contains noise that can obscure the crystal clear relationship between the inputs and outputs. You won't often have access to all the observations from a domain. You only work with a small sample of the data. Therefore, you harness randomness when evaluating a model, such as k-fold cross-validation, to fit and evaluate the model on different subsets of the available dataset. Do this to see how the model works on average rather than on a specific set of data. Machine learning algorithms use randomness when learning from a sample of data. This is a feature where the randomness allows the algorithm to achieve the better performing mapping of the data if the randomness was not used. Algorithms that use randomness are often called stochastic algorithms rather than just algorithms. This is because, although randomness is used, the resulting model is limited to a more narrow range. Some clear examples of randomness used in machine learning algorithms include the shuffling of training data prior to each training epoch and stochastic gradient descent, the random subset of input features chosen for split points in random forest algorithms, the random initial weights in artificial neural networks, and these are just a few. You can see that there are both sources of randomness that you must control for, such as noise in your data, and sources of randomness that you have some control over, such as algorithm evaluation and the algorithms themselves. The Python standard library provides a module named Random that offers a suite of functions for generating random numbers. Python uses a popular and robust pseudo-random number generator called the Mersenne twister. The pseudo-random number generator is a mathematical function that generates a sequence of nearly random numbers. It takes a parameter to start off the sequence, called the seed. The function is deterministic, meaning given the same seed, it will produce the same sequence of numbers every time. The choice of the seed number doesn't matter. The seed function will seed the pseudo-number random generator, taking an integer value as an argument, such as 1 or a 7. If the seed function is not called prior to using randomness, the default is to use the current time in milliseconds. The example demonstrates seeding this pseudo-random number generator, generates some random numbers, and then shows the reseeding of the generator that will result in the same sequence of numbers being regenerated. It can be useful to control the randomness by setting the seed to ensure that your code produces the same results every time, such as in a production model. For running experiments where randomness is used to control the confounding variables, a different seed may be used for each experimental run. Alright, let's talk about randomness and floating point variables. Random floating point values can be generated using the random function. Values will be generated in the range between 0 and 1, specifically the interval 0, 1. Values are drawn from the uniform distribution, meaning each value has an equal chance of being drawn. Our example generates 10 random floating point values. Lastly, let's talk about integers. Random integer values can be generated using the randint function. This function takes two arguments, the start and end of the range for the generated integer values. Random integers are generated within and including the start and end of the range values, specifically in the interval start-end. Random values are drawn from a uniform distribution. Our example generates 10 random integers between 0 and 10. In machine learning, you're likely to use libraries like scikit-learn and Keras. These libraries use NumPy under the covers, a library that makes working with vectors and matrices of numbers very efficient. NumPy also has its own implementation of a pseudo-random number generator and convenient wrapper functions. NumPy also implements the Mersenne twister pseudo-random number generator. Let's take a look at a few examples of generating random numbers and using their randomness with NumPy arrays. The NumPy pseudo-random number generator is different from the Python standard library pseudo-random number generator. It's easy for me to say. Importantly, seeding the Python pseudo-random number generator does not impact the NumPy pseudo-random number generator. It must be seeded and used separately. The seed function can be used to seed the NumPy pseudo-random number generator, taking the integer as the seed value. The example demonstrates how to seed the generator and how reseeding the generator will result in the same sequence of random numbers being generated. We've seen this before, now we're just doing it with the NumPy pseudo-random number generator. Running the example seeds the pseudo-random number generator, prints a sequence of random numbers, then reseeds the generator showing that the exact same sequence of random numbers is generated. Alright, let's take a look at one more, and we're going to look at how NumPy is used to generate some floating point numbers. An array of random floating point values can be generated with the rand_numpy function. If no argument is provided, then a single random value is created. Otherwise, the size of the array can be specified. The example on screen creates an array of 10 random floating point values, drawn from a uniform distribution. Let's talk about when to seed. There are times during predictive modeling projects when you want to consider seeding a random number generator. Let's look at two cases. The first is data preparation. Data preparation may use randomness, such as a shuffle of the data or a selection of values. Data preparation must be consistent so that the data is always prepared in the same way during fitting, evaluation, and when making predictions with the final model. The second case is data splits. The splits used in the data, such as train test split or k-fold cross-validation, must be made consistently to ensure that each algorithm is trained and evaluated in the same way on the same subsamples of data. You may wish to seed pseudo-random number generators once before each task or once before performing the batch of tasks. It generally doesn't matter which. Sometimes you may want an algorithm to behave consistently, perhaps because it's trained on exactly the same data each time. This may happen if an algorithm is used in a production environment. It may also happen if you're demonstrating an algorithm in a tutorial environment. In that case, it may make sense to initialize the seed prior to fitting the algorithm. A stochastic machine learning model will learn slightly differently each time it's run on the same data. This will result in a model with slightly different performance each time it's trained. As you've learned, you can fit the model to the same sequence of random numbers each time. However, when calculating a model, this is a bad practice, as it hides the inherent uncertainty within the model. A better approach is to evaluate the model in such a way the reported performance includes the measured uncertainty in the performance of the algorithm. You can do that by repeating the evaluation of the algorithm multiple times with different sequences of random numbers. The pseudo-random number generator could be seeded once at the beginning of the calculation, or it could be seeded with different seeds at the beginning of each evaluation. There are two core aspects to data uncertainty to consider here. Evaluating an algorithm on multiple splits of the data will give you insight into how the algorithm's performance varies with changes to the training and testing data. Evaluating an algorithm multiple times in the same splits of data will provide you with insight into how the algorithm's performance varies alone. As a general rule, I'd recommend reporting on both of these sources of uncertainty combined. This is where the algorithm is fit on different splits of the data each evaluation run and as a new sequence of randomness. The evaluation procedure can seed the random number generator once at the beginning of the procedure and be repeated X number of times to give a population of performance scores that can be summarized. This will give you a fair description of the model performance, taking into account variance both in the training data and in the model itself. Hello and welcome back. If you've been around machine learning, you've heard this a few times. The more data, the better. As a general rule, that's true, but why? There's a theorem in statistics and probability that supports the intuition that's a pillar of both fields and has important implications in applied machine learning. The name of this theorem is the law of large numbers. The law of large numbers is a theorem from probability and statistics that suggests that the average result from repeating an experiment multiple times will better approximate the true or expected underlying results. You can think of a trial of an experiment as one observation. The standalone or independent repetition of the experiment will perform multiple trials and lead to multiple observations. All the sample observations from an experiment are drawn from an idealized population of observations. Using statistical terms, you can say that as the size of samples increases, the mean value of the sample will better approximate the mean or expected value in the population. As the sample size goes to infinity, the sample mean will converge to the population. The more data, the better. In our example, we have a plot that compares the size of the sample to the error of the sample mean from a population mean. Generally, you can see the larger samples have less error, which is what we expect from the law of large numbers. Hello and welcome back. The central limit theorem is often quoted, but misunderstood pillar of statistics and machine learning. It's often confused with law of large numbers. Although the theorem may seem esoteric to beginners, and it will, it has important implications on how and why we make inferences about the skill of a machine learning model, such as whether one model is statistically better than another and confidence intervals on that model's skill. The theorem states that as the size of a sample increases, the distribution of the mean across the samples will more approximate a Gaussian distribution. Right, that sounds a little confusing, so let's visualize this. Imagine rolling a die lots of times. You expect to get, over a long period of time, an equal proportion of each roll. Next, let's do the same thing with 2 dice. Now you only have a 1 in 36 chance, which is around a 0.03 chance, of a 2 or a 12, because there's only one way you can make a 2. You need a 1 on both dice. However, a 7 is much more common. You have a 1 in 6 chance, or around a 0.16% chance, of a 7. Lastly, let's do the same thing with 3 dice. The chance of a 3, or an 18, is 1 in 216, which is 6 times 6 times 6. The chance of a 10 or 11 is much higher. Take note, as we moved from a single die to many die, the shape of the distribution has gone from flat to something that looks pretty close to a normal or Gaussian distribution. And you're only using 3 dice. Each time you add a die, the distribution gets closer to normal, and that's because of the central limit theorem. Hello and welcome back. Let's go ahead and do a demonstration. We're going to roll some die in the demonstration, but this time we're going to use some code. Remember that a die is a cube with a different number on each side, from 1 to 6. Each number has a 1 in 6 likelihood to turn up from a roll. The distribution of numbers that turn up from a dice roll is uniform given an equal likelihood. You can use the randint numpy function to generate specific random numbers for our dice rolls between 1 and 6. Running the example generates and prints out 50 dice rolls and the mean value of the sample. You can see the distribution of the dice rolls is about 3.4. You can also see that the mean of the sample is slightly wrong, which is to be expected in an estimate of the population mean. You can then repeat this process multiple times, such as 1,000. This will give you the result of 1,000 sample means. According to the central limit theorem, the distribution of these samples will be Gaussian. Well, let's find out. Running the example creates a histogram plot of the sample means. You can see the shape of the distribution is definitely Gaussian. Furthermore, the central limit theorem also states that as the size of the sample increase, in our case 50, then the better the sample means will approximate a Gaussian distribution. More samples, better Gaussian. Data must be interpreted in order to discover meaning. You can interpret data by assuming a specific structured outcome and use statistical methods to confirm or reject the assumption. The assumption is called a hypothesis, and the statistical tests used for these purposes are called statistical hypotheses tests. Whenever you want to make a claim about the distribution of data, or whether one set of results different from another set of results in applied machine learning, you must rely on statistical hypothesis tests. Data alone is not very interesting. It's the interpretation of the data that you're really interested in. In statistics, when you wish to start asking questions about the data and interpret the results, you are using statistical methods that provide a confidence or a likelihood about the answers. In general, this class of methods is called statistical hypothesis testing, or significant tests. The term hypothesis test may make you think about science, where you investigate a hypothesis. This is along the right track. In statistics, a hypothesis test calculates some quantity under a given assumption. The result of the test allows you to interpret whether the assumption holds or whether the assumption has been violated. Two concrete examples in machine learning are a test that assumes the data is normally distributed. Secondly, a test that assumes that 2 samples were drawn from the same underlying population. The assumption of a statistical test is called a null hypothesis, or hypothesis zero, H0 for short. It is often called the default assumption, or the assumption that nothing has changed. A violation of the test assumption is always called the first hypothesis, or hypothesis 1, or H1 for short. The result of a statistical hypothesis test must be interpreted for us to start making claims. This point may cause a lot of confusion for those who aren't well versed in statistics. There are 2 common forms that a result from a statistical hypothesis can take, and they must be interpreted in different ways. They are the p-value and critical values. Let's start with the p-value. You describe a finding as statistically significant by interpreting the p-value. For example, you may perform a student's t-test on 2 data samples and find that it's unlikely that the samples have the same mean. You reject the null hypothesis that the samples have the same mean at a chosen level of statistical significance or confidence. A statistical hypothesis test may return a value called a p or a p-value. This is a quantity that we can use to interpret or quantify the result of a test and either reject or fail the null hypothesis. This is done by comparing the p-value to a threshold value chosen beforehand called a significance level. Now, that seemed a little obtuse to me, so let's give another example. Hopefully this will help cement what p-value is. Suppose I give you a coin and claim that it's a fair coin, meaning the probability of heads is the same as tails. Now, for some reason you don't trust me. Maybe the coin is a bet between you and I, so you decide to test the coin. You flip the coin 100 times. You observe 99 heads and 1 tail. Do you trust me? Is the coin fair? Well, it could be. It is possible for a fair coin to exhibit this behavior. But what is the probability of getting such an extreme result? A statistician would measure this by computing the probability of 99 or more heads, because the fact is, at 100 flips, the probability of any individual count is relatively small. This probability is called a p-value. All right, let's talk about either rejecting or accepting the null hypothesis. To reject the null hypothesis is one of two possible outcomes of a hypothesis test. The other is failed to reject the null hypothesis. Both of these statements can be confusing to many people, including me. Let's try to clarify the concept to reject a null hypothesis. The null hypothesis states that there is no statistically significant difference. If the result of a statistical test is reject the null hypothesis, that means we conclude that there is something that is statistically significant. Let's take an example of a man proposing to a woman. In our example, a man asks a woman, "Will you marry me?" And she says, "I reject the null hypothesis." What is the null hypothesis to which she is referring? As we noted earlier, the null hypothesis says that there is no difference, change, or effect. Before his proposal, they were not engaged to be married. So, if there is to be no difference, change, or effect in the relationship as a result of his proposal and her response, the null hypothesis would say that they are not engaged to be married. However, if she rejects the null hypothesis, this indicates that she does want to be married because there is a significant change in the outcome. In this case, when she says, "I reject the null hypothesis," she actually means, "Yes, I want to be married to you." Hello and welcome back. A sample of data will always form a distribution, and by far the most well-known distribution is the Gaussian distribution, often called the normal distribution. This distribution describes the grouping or the density of the observations, called the probability density function. You can also calculate the likelihood of an observation having a value equal or lesser to the value given. A summary of these relationships between observations is called the cumulative density function. You can think of a distribution as a function that describes the relationship between observations in a sample space. For example, you may be interested in the age of humans, with individual age representing the observations in the domain, and ages from 0 to 125 represent the sample space. The distribution is a mathematical function that describes the relationship of observations of different heights. A distribution is simply a collection of data, or scores, on a variable. Usually, these scores are arranged in order from smallest to largest, and then they are presented graphically. Many data conform to well-known and well-understood mathematical functions, such as Gaussian distributions. A function can fit the data with a modification of parameters of the function, such as the mean or standard deviation in the case of a Gaussian distribution. Once a distribution function is known, it can be used as shorthand for describing and calculating related quantities, such as likelihoods of observations, and the plotting relationship between observations in the domain. Hello and welcome back. In this lecture, let's talk about density functions. Distributions are often described in terms of their density or density functions. Density functions are functions that describe how the proportion of data or the likelihood of the proportion of data of the observations change over the range of the distribution. Two types of density functions are probability density functions and cumulative density functions. PDFs, or probability density functions, calculate the probability of observing a given value. CDFs, or cumulative distribution functions, calculates the probability of an observation equal to or less than a value. A PDF can calculate the likelihood of a given observation in a distribution. It can also be used to summarize the likelihood of observations across the distribution sample space. Plots of PDFs show a familiar shape of the distribution, such as a bell curve or a Gaussian distribution, in our example. Distributions are often defined in terms of their probability density functions with the associated parameters. Cumulative density functions, or CDFs, are a different way of thinking about the likelihood of the observed values. Rather than calculating the likelihood of given an observation with the PDF, the CDF calculates the cumulative likelihood for the observation and all prior observations in that space. It allows you to quickly understand and comment on how much the distribution lies before and after a given value. A CDF is often plotted as a curve from 0 to 1 for the distribution. Both PDFs and CDFs are continuous functions. Hello and welcome back. A sample of data can be checked to see if it's random by plotting it and checking for the familiar normal shape, or by using statistical tests. If the sample of observations of a random variable are normally distributed, then they are summarized by just the mean and variance, calculated directly on the samples. You can calculate the probability of each observation using the probability density function. A plot of these values will give you the telltale bell shape. You can define a normal distribution using the norm SciPy function, and then calculate properties such as PDF, CDF, and more. Running the example first calculates the probability integers for a range of 30 to 70, and creates a line of plot values and probabilities. The plot shows the Gaussian or bell shape with the peak of the highest probability around the expected value or mean of 50, with a probability of about 8%. The cumulative probabilities are then calculated for observations over the same range, showing that at the mean, we have covered about 50% of the expected values and are very close to 100% after the value of about 65 or 3 standard deviations from the mean. In fact, the normal distribution has a heuristic or rule of thumb that defines the percentage of data covered by a range by the number of standard deviations from the mean. It's called the 68, 95, and 99.7 rule, which is the approximate percentage of data covered by the ranges defined by 1 or 2 or 3 standard deviations from the mean. We've seen this earlier in the course. For example, in our distribution with a mean of 50 and a standard deviation of 5, you would expect that 95% of all the data to be covered by the values that are 2 standard deviations from the mean, or between 40 and 60. You can confirm this by calculating the exact values using the percentage point function. The middle 95% would be defined by the percentage point function of a value of 2.5 at the low end and 97.5 at the high end, where 97.5 to 2.5 gives the middle 95%. Running our example gives the exact outcomes that define that middle 95% of expected values that are very close to our standard deviation-based heuristics of 40 and 60. Hello and welcome back. William Gossett was an English statistician who worked for the Guinness Brewery. He developed different methods for the selection of the best yielding varieties of barley, an important ingredient when making beer. Gossett found big samples tedious and hard to work with, so he tried to develop a way to extract small samples but still come up with meaningful predictions. He was a curious and productive researcher and published several papers that are still relevant today. However, due to the Guinness policy, he was not allowed to sign the papers with his own name. Therefore, all his work showed up under his pen name, Student. The t-distribution is a family of distributions that look almost identical to the normal distribution curve, only a bit shorter and a bit fatter. The t-distribution is used instead of the normal distribution when you have small samples. The larger the sample size, the more the t-distribution looks like a normal distribution. In fact, for samples larger than 20, more degrees of freedom, the distribution is almost exactly like a normal distribution. Although you may not use Student's t-distribution directly, you may estimate values from the distribution required as parameters in other statistical methods, such as statistical significance tests. The key to using the t-distribution is knowing the desired number of degrees of freedom. The number of degrees of freedom describes the number of pieces of information used to describe the population quantity. For example, the mean has n degrees of freedom, as all n observations in the sample are used to calculate the estimate of the population mean. A statistical quantity that makes use of another statistical quantity in its calculation must subtract 1 degrees of freedom, such as the use of the mean in the calculation of sample variance. Observations in Student's t-distributions are calculated from observations in a normal distribution in order to describe the interval for the population mean in a normal distribution. Hello and welcome back. The chi-squared distribution is a term in statistics and probability theory. It's used for goodness of fit of an observed distribution versus a theoretical distribution. The chi-squared distribution is also used in statistical methods that are drawn from a Gaussian distribution to quantify the uncertainty. For example, the chi-squared distribution is used for the chi-squared statistical test for independence. In fact, the chi-squared distribution is used for the derivation of the Student's t-distribution. The chi-squared distribution has one parameter, and that's degrees of freedom, where chi is an observation that has a chi-squared distribution. Similar to a Student's t-distribution, data does not fit a chi-squared distribution. Instead, observations are drawn from this distribution in the calculation of statistical methods for a sample of Gaussian data. All right, let's jump over and take a look at some code. SciPy, or Scientific Python, provides the stats-chi2 module for calculating statistics for a chi-squared distribution. I think I've been saying chi for the last 10 lessons. It's actually chi. I hate words like this. The chi2 PDF function can be used to calculate the chi-squared distribution for a sample between 0 and 50 with 20 degrees of freedom. Recall that the sum of the squared values must be positive, hence the need for a positive sample space. In our example, we are calculating the chi-squared PDF, and it presents a line plot for us. With 20 degrees of freedom, you can see that the expected value of the distribution is just short of the value 20 on the sample space. This is intuitive if we think most of the density in the Gaussian distribution lies between -1 and 1, and then the sum of the squared random observations from the standard Gaussian distribution would sum to just under the number of degrees of freedom, in this case 20. Although the distribution has a bell shape, the distribution is not symmetric. The chi-squared CDF function can be used to calculate the cumulative density function over the sample space. Running our example creates a plot of the cumulative density function for the chi-squared distribution. This distribution helps you see the likelihood of the chi-squared value around 20, with that fat tail to the right of the distribution that will continue on long after the end of the plot. Hello and welcome back. It's not common, if not standard, to interpret the results of statistical hypothesis tests using p-values. However, not all implementations of statistical tests return p-values. In some cases, you might use an alternative, such as a critical value. In addition, critical values are used when estimating the expected intervals for observations from a population, such as tolerance intervals. In this section, you're going to discover critical values and why they are important and how to use them. A statistic calculated by a statistical hypothesis test can be interpreted using critical values from the distribution of test statistics. Some examples of statistical hypothesis tests and their distributions from which the critical values can be calculated are z-tests, students' t-tests, chi-squared tests, and ANOVAs. Don't worry, we'll talk about the ones we haven't gone over coming up. Critical values are also used when defining intervals for expected or unexpected observations and distributions. Calculating and using critical values may be appropriate when quantifying the uncertainty of estimated statistics or intervals such as confidence intervals and tolerance intervals. All right, let's define critical value. A critical value is a value which helps you decide whether or not you're going to accept or reject a null hypothesis. This value changes as you change the level of significance. At a certain level of significance, it depends on the distribution of the test statistic and degrees of freedom. Your decision to either reject or accept a null hypothesis based on critical values will depend on which type of hypothesis testing you are doing. For example, one-tail or two-tail hypothesis testing. All right, that definition was a little obtuse, so let's look at the anatomy of a critical value. I hope this visualization will make the concept more lucid. The first point is that it's used in hypothesis testing. All right, the second point is it assumes a normal or Gaussian distribution. Thirdly, there's an acceptance region and a rejection region. On the example, R is the rejection region and A is the acceptance region. Lastly, the line separating those regions is the critical value. All right, next let's take a look at the steps involved from a high level. The first step in the process is finding the critical value. Let's say that our critical value is 2.0. The second step in the process is to run your test. In this example, let's say that our value is a 2.9. Because this is a bell curve, you know the mean is 0. From the chart at the bottom, I apologize, it's a little blurry, are the positive and negative standard deviations. Let's go ahead and plot that 2.9 on the chart. When that value is plotted, you can see it falls in the rejection region. That means, in this example, you would reject the null hypothesis. The critical value allows you to either accept or reject the null hypothesis. Hello and welcome back. In hypothesis testing, you are asked to decide if a claim is true or not. For example, if someone says, all Floridians have a 50% increased chance of melanoma, it's up to you to decide if the claim holds merit. Calculated critical values are used as a threshold for interpreting the results of statistical tests. The observation values in a population beyond the critical value are often called the critical region or the region of rejection. A statistical test may be one- or two-tailed. A one-tailed test allows you to determine if the mean is greater or less than another mean, but not both. A direction must be chosen prior to testing. In other words, a one-tailed test will tell you the effect of a change in one direction and not the other. Think of it this way. If you're trying to decide if you would buy a brand name product or a generic product at a local drugstore, a one-tailed test of the effectiveness of the product would only tell you if the generic product worked better than the name brand. You would have no insight into whether the product was equivalent or worse. Since a generic product is cheaper, you could see what looks like minimal impact, but is in fact negative impact, meaning it doesn't work very well at all. However, you go ahead and purchase that generic product because it's cheaper. A two-tailed test allows you to determine if the two means are different from one another. A direction doesn't have to be specified prior to testing. In other words, a two-tailed test will take into account the possibility of both positive and negative effect. All right, let's head back to the drugstore example. If you were doing a two-tailed test on a generic drug against a name brand product, you would have insight into whether the effectiveness of the product was equivalent or worse than the name brand product. In this instance, you can make a more educated decision because if the generic product is equivalent, you would purchase it at a cheaper price. However, if it is far less effective than the name brand product, then you'd probably shell out the extra money to buy the name brand product. So when should you use a two-tailed test? Two-tailed tests are used when you are willing to accept any of the following. One mean being greater, lower, or like another. Hello and welcome back. In order to calculate a critical value, you require a function, given a significance, will return an observation value from the distribution. Specifically, you require the inverse of the cumulative density function. Where given a probability, you are given the observation value that is less or equal to the probability. This value is called the percent point function, or more generally, the quantile function. A percent point function returns the observation value for the provided probability that is less or equal to the provided probability from the distribution. A value from this distribution will be equal or less than the value returned from the PPF with the specified probability. All right, let's work through three distributions which are commonly used to calculate critical values. I think this will help cement the concept. You're going to work through three examples here: a Gaussian distribution, a student's t-distribution, and a chi-square distribution. You calculate the percent point function in SciPy using the PPF function on a given distribution. It should be noted that you can calculate the PPF using the inverse survival function, ISF, in SciPy also. The first example calculates the percent point function for 95% on the standard Gaussian distribution. Running the example first prints the value of 95%, or less of the observations from the distribution of about 1.65. This value is then confirmed by retrieving the probability of the observations from the CDF, which returns 95%, as expected. You can see that the value of 1.65 aligns with the expectation in regard to the number of standard deviations from the mean that cover 95% of the distribution in our old 68, 95, 99.7 rule. The second example calculates the percentage point function for 95 of the standard student's t-distribution within 10 degrees of freedom. Running the example returns the value of about 1.81 or less that covers 95% of the observations from a chosen distribution. The probability of the value is then confirmed, with a minor rounding error, via the CDF. Our last example calculates the percentage point function for 95% of the standard chi-square distribution, again within 10 degrees of freedom. Running the third example then calculates the value of 18.3 that covers 95% of the observations from that distribution. The probability of this observation is then confirmed using it as the input to the CDF. Hello and welcome back. Correlation is essentially a measure of how closely two variables are related to each other. The higher the correlation, the more closely the two variables are related to each other. If an experiment or study is designed to determine which factors might influence other factors of interest, you are testing the correlation between these factors. For example, you may have noticed that men prefer Diet Cola and women prefer mineral water. Providing this type of correlation allows you to establish a predictive relationship for future behavior. The concept of correlation was first attributed to Sir Charles Galton, a cousin of Charles Darwin, in the 1880s. Galton spent many years studying the patterns related to the physical traits in humans and what behaviors could be predicted by them. He later developed the concept of regression. He was able to apply statistical scales to his observations that could prove or disprove relationships between them. Our example on screen shows the difference between correlation and causation, two terms that are used together but often confused in their usage. It can be useful in data analysis and modeling to better understand the relationship between two variables. This statistical relationship between the two variables is referred to as their correlation. There are three things correlations can be, or correlation can be positive, meaning both variables move in the same direction. A correlation can be negative, meaning that when one variable value increases, the other variable's value decreases. And lastly, a correlation can be neutral or zero, meaning that the variables are unrelated. The performance of some algorithms can deteriorate if two or more variables are tightly related. This is called multicollinearity. An example is in linear regression, where one of the offended correlated values should be removed in order to improve the skill of the model. You may also be interested in the correlation between input variables with the output variable in order to provide insight into which variables may or may not be relevant as input for developing a model. Let's craft a quick demo that shows a strong positive correlation between two variables. The first thing I'll do is to generate 1,000 samples of two variables with a strong positive correlation. The first variable will be random numbers drawn from a Gaussian distribution with a mean of 100 and a standard deviation of 20. The second variable will be values from the first variable with Gaussian noise added with a mean of 50 and a standard deviation of 10. You'll use the rand function to generate random Gaussian values with a mean of 0 and a standard deviation of 1. Then you'll multiply the results by your own standard deviation and add the mean to shift the values into the preferred range. The pseudo-random number generator is seeded to ensure you get the same sample of numbers each time the code is executed. The scatter plot shows how the two variables are created. Because this is a contrived dataset, you know that there is a strong positive correlation between the two variables. This is clear when you review the generated scatter plot, where you can see the increasing trend. Hello and welcome back. Variance measures how far your data is spread out. If variance is 0, it means all the data points are the same. Technically, you can say that variance is nothing but the average of the square differences from the mean. If you take the square root of variance, you get standard deviation. If you knew the mean and variance of a one-dimensional dataset, you could then visualize the shape of the data. Variables can be related by linear relationships. This is a relationship that is consistently additive across the two data samples. This relationship can be summarized between two variables, called covariance. If the dimension of the data is more than 1, mean and variance are not enough to visualize the geometry of the data. You need to know the orientation of the data as well. Covariance tells us the orientation of those data points. All right, let's work through an example. Let's calculate the covariance of a matrix for two variables in our test problem. The covariance and covariance matrix are used widely within statistics and multivariate analysis to characterize the relationships between two or more variables. Running the example calculates and prints the covariance matrix. Because the dataset was contrived with each variable drawn from a Gaussian distribution, and the variables being linearly correlated, covariance is a reasonable method for describing the relationship. The covariance between two variables is 389.75. You can see that it's positive, suggesting that the variables change in the same direction as you'd expect. A problem with covariance as a statistical tool alone is that it's challenging to interpret. This leads us to Pearson's correlation coefficient, which we'll look at next. The Pearson's R correlation coefficient, named for Carl Pearson, can be used to summarize the strength of the linear relationship between two data samples. The Pearson's R correlation coefficient is calculated as the covariance of the two variables divided by the product of the standard deviation of each sample. Again, that sounds complicated, but it's really not. In our example, as age goes up, yearly income goes up. Pearson's R is simply a measure of the strength of the linear relationship between two variables, in our case, age and income. In the example, you can easily draw a line plotting the relationship. Pearson's R is always between 1 and -1. For example, your R would be 1 when you have a perfect positive linear relationship between the two variables. As x increases, y increases with it. The second case is R of -1. When you have an R of -1, you have a perfect negative linear relationship between the two variables. Additionally, you can have an R of 0, which means there is no relationship at all between the two variables. The Pearson's R SciPi function can be used to calculate the Pearson's R correlation coefficient between the two data samples with the same length. You can calculate the correlation between the two variables in the test problem. Running the example calculates and prints the Pearson's correlation coefficient and interprets the p-value. You can see that the two variables are positively correlating, and the correlation is about 0.88. This suggests a high level of correlation, as you expected. The Pearson's R correlation coefficient can be used to evaluate the relationship between more than two variables. This can be done by calculating a matrix of the relationship between each pair of variables in the dataset. The result is a symmetric matrix called a correlation matrix, with a value of 1 along the diagonal, as each column is always perfectly correlated with itself. Tests of statistical significance are divided into two separate sections. They are parametric and non-parametric statistical tests. The hallmark for each is based on the distribution of the data. Parametric statistical tests assume that the data sample will be drawn from a specific distribution, and that distribution is the normal distribution, or a Gaussian distribution. Because it's so common for the data to fit that distribution, parametric statistical methods are more commonly used. Non-parametric statistical tests are drawn from a skewed data distribution. On our screen are a few common qualities of each type of test. Again, the core aspect of each is based on the distribution of the data. A typical question we may have about two or more samples of data is whether they have the same distribution. Parametric statistical significance tests are those statistical tests that assume the data was drawn from a Gaussian distribution. That is, a data distribution with the same mean and standard deviation. The parameters of the distribution. Alright, before you dive into specific examples of these parametric significance tests, let's define a test dataset that you can use to demonstrate each test. You're going to generate two samples drawn from different distributions. Each sample will be drawn from a Gaussian distribution. You're going to use the rand_in numpy function to generate a sample of 100 Gaussian random numbers, and each sample with a mean of 0 and a standard deviation of 1. Observations in the first sample are scaled to a mean of 50 and a standard deviation of 5. Observations in the second sample are scaled to a mean of 51 and a standard deviation of 5. You expect the statistical test to discover that the samples were drawn from differing distributions, although the sample size of 100 observations per sample will add some noise to this decision. Running the example generates the data samples, then calculates and prints the mean and the standard deviation for each sample, confirming their different distributions. In the next lesson, you're going to use this dataset for several parametric significance tests. Hello and welcome back. The assumption of a null hypothesis of a test is that the means of the two populations are equal. A rejection of this hypothesis indicates that there is sufficient evidence that the means of the populations are different, and in turn that the distributions are not equal. The student's t-test is available via Python using the test_ind scipy function. The function takes two samples as arguments and returns the calculated statistic and the p-value. You can demonstrate the student's t-test on a test problem with the exception that the test discovers the differences in the distribution between the two independent samples. Running our example calculates the student's t-test on the generated data samples and then prints the statistic and the p-value. The interpretation of this statistic finds that the sample means are different, with a significance of about 5%. You may wish to compare the means between two data samples that are related in some way. For example, the data samples may represent two independent measures or evaluations of the same object. These data samples are repeated or dependent and are referred to as paired samples or repeated measures. Because the measures are not independent, we cannot use the student's t-test. Instead, you can use a modified version of the test that corrects for the fact that the data samples are dependent, called the paired student's t-test. The test is simplified because it no longer assumes that there is a variation between the observations, that the observations were made in pairs, before and after a treatment on the same subject or subjects. The default assumption, or null hypothesis of the test, is that there is no difference in the means between the samples. The rejection of the null hypothesis indicates that there is enough evidence that the sample means are different. The paired student's t-test can be implemented in Python using the tt_test_rel scipy function. As with the unpaired version, the function takes two data samples as arguments and returns the calculated statistic and the p-value. In our example on screen, we have a paired student's t-test on our dataset. Although the samples are independent and not paired, you can pretend for the sake of demonstration that the observations are paired and can calculate the statistic. Running the example calculates and prints the test statistic and the p-value. The interpretation of the result suggests that the samples have different means and therefore different distributions. There are situations where you may have multiple independent data samples. You can perform the student's t-test pairwise on each combination of the data samples to get an idea of which samples have different means. This can be difficult if you are only interested in whether all the samples have the same distribution or not. To answer this question, you can use the analysis of variance test, or ANOVA for short. ANOVA is a statistical test that assumes that the mean across the two or more groups are equal. If the evidence suggests that this is not the case, the null hypothesis is rejected and at least one data sample has a different distribution. The test requires that the data samples are Gaussian distributions, that the samples are independent, and that all the data samples have the same standard deviation. The ANOVA test can be performed in Python using the f1way scipy function. The function takes two or more data samples as arguments and returns the test statistic and f-value. You can modify the test problem to have two samples with the same mean and a third sample with a slightly different mean. You would then expect the test to discover that at least one sample has a different distribution. Running the example calculates and prints the test statistic and the p-value. The interpretation of the p-value correctly rejects a null hypothesis indicating that one or more sample means are different. Hello and welcome back. Statistical hypothesis tests report on the likelihood of the observed results given an assumption, such as no association between variables or no difference between groups. Hypothesis tests do not comment on the size of the effect if the association or the difference is statistically significant. This highlights the need for a standard way of calculating and reporting a result. Effect size methods refer to a suite of statistical tools for quantifying the size of an effect in the results of experiments that can be used to complement the results from statistical hypothesis tests. An effect size refers to the size or magnitude of an effect or result as it would be expected to occur in a population. The effect size is estimated from samples of data. More simply put, effect size is a way of describing, in a normalized way, the magnitude of the difference between two groups. Why is effect size important? It's a way to use the same measuring stick to show the importance of the difference between one group or another group. When you look at data samples, you need to take into account the spread of the data samples when you compare them. It's common to organize effect size statistical methods into groups based on the type of effect that is to be quantified. Two main groups of methods for calculating effect size are association. These are statistical methods for quantifying an association between variables, like correlation, and difference. These are statistical methods for quantifying the difference between variables, like the difference between means. The result of an effect size calculation must be interpreted, and it depends on the specific statistical methods used. A measure must be chosen based on the goal of the interpretation. Three types of calculated results include: the first is a standardized result. The effect size is a standard scale, allowing it to be interpreted generally regardless of application, like the Cones calculation. Secondly, there's original unit result. The effect size may use the original units of the variable, which can aid in the interpretation within a domain. For example, the difference between two sample means. Lastly, there's unit-free results. The effect size may not have units such as count or proportion. For example, a correlation coefficient. The association between variables is often referred to as the R family of effect size methods. This name comes from perhaps the most common method for calculating the effect size, called Pearson's correlation coefficient, also referred to as Pearson's R. The Pearson's correlation coefficient measures the degree of the linear association between two real-valued variables. It's a unit-free effect size measurement that can be interpreted in a standard way. The calculations for the disparate levels are listed on the screen. The Pearson's correlation coefficient can be calculated in Python using the Pearson's R scipy function. The example on our screen demonstrates the calculation of the Pearson's correlation coefficient to quantify the size of the association between two samples of a random Gaussian distribution, where one of the samples has a strong relationship with the second. Running our example calculates and prints the Pearson's correlation between the two samples. You can see that the effect shows a strong positive relationship between those two samples. Statistical power is one piece of the puzzle that has four related parts. The first of those parts is effect size. The quantified magnitude of a result present in the population is effect size. Effect size is calculated using a specific statistical measure, such as Pearson's correlation coefficient, for the relationship between two variables. Next up is sample size. This is the number of observations in the sample. Next up is significance. This is the significance level used in the statistical test. It's often set to around 5% or 0.05. Fourthly is statistical power. This is the probability of accepting the alternative hypothesis if it's true. All four variables are related. For example, a larger sample size can make an effect easier to detect, and the statistical power can be increased in a test by increasing the significance level. A power analysis involves estimating one of these four parameters given values for the other three parameters. For example, the statistical power can be estimated given an effect size, sample size, and significance. Alternatively, the sample size can be estimated given a different desired levels of significance. Perhaps the most common use of power analysis is in the estimation of the minimum sample size required for an experiment. As a practitioner, you can start with sensible defaults for some of the parameters, such as a significance level of 0.05 and a power level of 0.80. You can then estimate a desirable minimum effect size, specific to your experiment being performed. A power analysis can be used to estimate the minimum sample size required. In addition, multiple power analysis can be performed to provide a curve of one parameter against another. Now, more elaborate plots can be created varying these parameters. This is an extremely useful tool in experimental design. Hello and welcome back. Data is the currency of applied machine learning. Therefore, it is important that it's both collected and used effectively. Data sampling refers to the statistical methods for selecting observations from a domain with the objective of estimating a population parameter, whereas data resampling refers to the methods for using a collected data set to improve the estimate of the population parameters and to help quantify the uncertainty of the estimate. Both data sampling and data resampling are methods that are required in a predictive modeling problem. Each row of data represents an observation about something in the world. When working with data, you don't often have access to all the possible observations. A population is a collection of elements that has characteristics in common. A sample is a subset of the population. The process of selecting a sample is known as sampling. There are many sampling techniques that are grouped into two categories: probability sampling and non-probability sampling. The difference in the two lies in whether the sample selection is based on randomization or not. With randomization, every element has an equal chance of being selected. Probability sampling techniques use randomization to make sure that every element of the population gets an equal chance to be part of that selected group. Non-probability sampling does not rely on randomization. This technique is more reliant on the researcher's ability to select elements from the sample. With this approach, sampling may be biased, and it makes it difficult for all the elements of the population to be part of the sample equally. Statistics sampling is a large field of study, but in applied machine learning, there are three types of sampling you're likely to encounter. Simple random sampling. Samples are drawn from a uniform probability from the domain. Systemic sampling. Samples are drawn using a pre-specified pattern, such as intervals. And stratified sampling. Samples are drawn with a pre-specified categories, they're strata. Although there are many more common techniques in this field, these are the three you're likely to encounter in the applied machine learning space. Sampling requires that you make a statistical inference about the population from a small set of observations. You can generalize properties from the sample to the population. This process of estimation and generalization is much faster than working with all the possible observations, but it's going to contain errors. In many cases, you can't quantify the uncertainty of the estimates and add error bars, such as confidence intervals. There are many ways to introduce errors to your data sample. Two main types of errors include selection bias and sampling errors. Selection bias is caused when the method of drawing the observation skews the sample in some way, and a sampling error is caused due to the random nature of drawing observations skewing the samples in some way. Now, other types of errors may be present, such as systemic errors in the way observation measurements are made. In this case, the statistical properties of the sample may be different from what would be expected in the idealized population, which in turn may impact the properties of the population that are being estimated. Simple methods such as reviewing raw observations, summary statistics, and visualizations can help expose simple errors, such as measurement corruption and the over- or underrepresentation of the class of observations. Nevertheless, care must be taken both when sampling and when drawing conclusions about the population while sampling. Hello and welcome back. Once you have a data sample, it can be used to estimate the population parameter. The problem is that you only have a single estimate of the population parameter, with little idea of the variability or the uncertainty in the estimate. One way to address this is by estimating the population parameter multiple times from a data sample. This is called resampling. Statistical resampling methods are procedures that describe how to economically use available data to estimate a population parameter. The result can be both more accurate estimates of the parameters, such as taking the mean of the estimates, and a quantification of the uncertainty of the estimate, such as adding confidence intervals. Resampling methods are very easy to use, requiring little mathematical knowledge. A downside of methods like this are they are computationally very expensive, requiring tons, hundreds, or even thousands of resamples in order to develop a robust estimate of the population. The problem with this is that there will be some relationships between the samples as observations that will be shared across multiple subsamples. This means that the subsamples and the estimated population parameters are not strictly identical and independently distributed. This has implications for a statistical test performed on a sample of estimated population parameters downstream. For example, paired statistical tests may be required. In the applied machine learning space, two commonly used sampling methods you'll encounter are k-fold cross-validation and bootstrap. With bootstrap, samples are drawn from the dataset with replacement, allowing the sample to appear more than once in the sample. Secondly, there's k-fold cross-validation. A dataset is partitioned into k groups, where each group is given the opportunity of being used as held-out test sets, leaving the remaining group in the training set. The k-fold cross-validation method specifically lends itself to use in the evaluation of predictive models that are repeatedly trained on the subset of data and evaluated on a second held-out subset of data, i.e. the testing and training sets. The bootstrap method can be used for the same purpose, but it's a more general and simpler method intended for estimating a population parameter, and thus not used as often as the gold standard, which is k-fold cross-validation. Hello and welcome back. The bootstrap method is used for estimating quantities about a population by averaging estimates from multiple small data samples. Importantly, samples are constructed by drawing observations from large data samples, one at a time, and returning them to the data sample after they've been chosen. This allows a given observation to be included in each small sample more than once. This approach to sampling is called sampling with replacement. Alright, let's craft the steps in this process. Step 1. Randomly choose a sample from the population. Step 2. We write it down. Step 3. We put it back in the sample. Yes, this means an observation can be chosen more than one time. Alright, let's look at the process using some real data samples. I think this will help cement the process. On the first slide, you have a population with 6 samples. Not much of a population, however, this is only for demonstration purposes. You extract one observation, one row, from your population. On the next slide, you take that row and put it back into the population. Then you repeat that process any n number of times. This time, you pull out one more observation and then put it back. Next, you do it one more time. This time, take note that you've pulled out the same sample twice. This can happen because on each iteration, you're putting the sample back into the population. Your final result is one bootstrap sample with 3 observations. Hello and welcome back. You don't have to implement the bootstrap method manually. The scikit-learn library provides an implementation that will create a single bootstrap sample of a dataset. The resample scikit-learn function can be used. It takes as arguments the data array, whether or not to sample with replacement, the size of the sample, and the seed of the pseudo-random number generator used prior to the sampling. For example, you can create a bootstrap that creates a sample with 4 observations and uses one value for the pseudo-random number generator. Unfortunately, the API doesn't include any mechanism to easily gather out-of-bag observations that could be used as a test set to evaluate the fit model. At least in the univariate case, you can gather the out-of-bag observations using a simple Python list comprehension. Running the example prints the observations in the bootstrap sample, and those observations that are in the out-of-bag sample also. Cross-validation is a resampling procedure used to evaluate machine learning models on limited data. In cross-validation, you partition the dataset into k-bins. Because you divide the dataset into separate bins, this kind of cross-validation is known as k-fold cross-validation. The k is simply the number of segments, called bins, the dataset is divided into. In the sample on screen, there are 5 bins or folds. If you have 100 samples or rows in your dataset, each bin will be 20 samples. In machine learning, rows are often referred to as samples or observations. The choice of k is usually 5 or 10, but there's no formal rule. As k gets smaller, the difference in size between the training set and the resampling subsets gets smaller. As the difference decreases, the bias of the technique becomes smaller. With each sample on screen, you'll train the model on 4 bins or folds and test the model on 1 bin or fold. Each time the model is run, it's run in the entire dataset, except for the bin or fold that's left out for testing. Each of these runs is referred to as an iteration. Each iteration will have different subsets of the data set aside for testing. Once all the iterations have been completed, the model will have been tested on the entire dataset, each time leaving out the subset of data for testing. Upon completion, an average of the scores of each iteration will be taken, and that score will be used for the model. The k-fold scikit-learn class can be used. It takes as arguments the number of splits, whether or not to shuffle the sample, and the seed of the pseudo-random number generator used prior to the shuffle. One of the great features of Python is its ability to combine libraries. Regardless of the model you choose, you can use scikit-learn's k-fold implementation to partition your data. Hello and welcome back. There are a number of variations of the k-fold cross-validation procedure. 4 commonly used variations are train test split. Train test split is a function in scikit-learn for splitting the data into 2 separate arrays, into 2 subsets of data, one for training and one for testing purposes. With this function, you don't have to divide the dataset manually. Next is LOOVC. This stands for leave one out cross-validation. Taken to another extreme, K may be set to the total number of observations in the dataset, such that each observation is given a chance to be held out of the dataset. Next, there's stratified. Splitting the data into folds may be governed by criteria, such as ensuring that each fold has the same proportion of observations with a given categorical value, such as a class outcome value. This is called stratified cross-validation. Lastly is repeated. This is where a k-fold cross-validation procedure is repeated n number of times, where importantly, the data sample is shuffled prior to each repetition, which results in a different split for each sample. Hello and welcome back. In this lesson, let's take a look at another resampling approach called train-test split. This approach does the same thing as k-fold cross-validation, just a little differently. With this approach, the data is segmented into two bins, one for training and one for testing. Now you might be thinking, if k-fold cross-validation is the gold standard, then why would we use train-test split? A few reasons. Firstly, you get to see how another resampling approach works. Secondly, for many, this is often easier to understand and implement. And lastly, because it's often an interview question. Okay, let's get started importing the libraries. Take note that train-test split lives within the model selection within the scikit-learn library. The rest of those libraries you should be familiar with from the previous lesson. Next, let's craft a variable to hold our data. After that, let's take a look at the data. Yeah, it looks good. It's all array and it's all numbers. Next, let's separate our data so the model knows the target variable and the data we're going to train and test on. In the next cell is train-test split. You've created a seed for reproducibility and created a variable to hold the testing part of the data. The 20 represents the amount of data in a percentage that you're holding back for testing. So, if you're holding back 20% of your data for testing, then 80% is for training. Next up, you'll create a variable to hold your XGBoost model and fit it to your training data. In the last cell, you're going to test that model on that 20% you set aside and output the score for the model. I'll often develop a model with train-test split and then use k-fold on the fresh data when I believe I've tuned the model and it's ready for production. Hello and welcome back. Statistical hypothesis tests can be used to indicate whether the difference between the two samples is due to random chance, but can't comment on the size of the difference. A group of new methods referred to as new statistics are seeing an increased usage instead of or in addition to p-values in order to quantify the magnitude of effects and the amount of uncertainty for estimated values. This group of statistical methods is referred to as estimation statistics. Statistical hypothesis testing and the calculation of p-values is a popular way to present and interpret results. Tests like the student's t-test can be used to describe whether two samples have the same distribution. They can help interpret whether the difference between two sample means is likely real or due to random chance. Although they are widely used, they do have some problems. For example, calculated p-values are easily misused and misunderstood. Additionally, there's always some significant difference between samples, even if that difference is tiny. Interestingly, in the last few decades, there's been a pushback against the use of p-values in presentation of research. For example, in the 1990s, the Journal of Epidemiology banned the use of p-values. Many related areas in medicine and psychology have followed suit. Although p-values may still be used, there's a push towards the presentation of results using estimation statistics. Hello and welcome back. Let's go ahead and define estimation statistics. Estimation statistics refer to methods that attempt to quantify a finding. This might include quantifying the size of an effect or the amount of uncertainty for a specific outcome or result. Estimation statistics is a term to describe the three main classes of methods. The three main classes include, number one, effect size. These are methods for quantifying the size of an effect given a treatment or intervention. Number two, interval estimation. These are methods for quantifying the amount of uncertainty in a value. And number three, meta-analysis. These are methods for quantifying the findings across multiple similar studies. You will look at each of these groups of methods in more detail in the following section. Although they are not new, they are being called new statistics given their increased usage in research literature over statistical hypothesis testing. Where statistical hypothesis tests talk about whether the sample comes from the same distribution or not, estimation statistics can describe the size and the confidence of the difference. This allows you to comment on how different one method is from another. The main reason that the shift from statistical hypothesis methods to estimation systems is occurring is that they are easier to analyze and interpret in the context of domain or research questions. The quantified size of the effect and uncertainty allows claims to be made that they are easier to understand and use. Hello and welcome back. In this brief lesson, let's talk about effect size. The effect size describes the magnitude of a treatment or the difference between two samples. A hypothesis test can comment on whether the difference between samples is a result of chance or real, whereas an effect size puts a number of how much the samples differ. Measuring the size of an effect is a big part of applied machine learning, and in fact research in general. There are two main classes or techniques to quantify the magnitude of an effect. They are association. Association is the degree to which the samples change together. The second one is difference. This is the degree to which samples are different. For example, association effect size include calculations of correlation, such as Pearson's correlation coefficient and R-squared coefficient of determination. They may quantify the linear or monotonic way that observations in two samples change together. Different effect size may include methods such as Cohen's statistic that provide a standardized measure for how the means of two populations differ. They see quantification for the magnitude of the difference between observations of two samples. Hello and welcome back. Interval estimation refers to statistical methods for quantifying the uncertainty for an observation. Intervals transform a point estimate into a range that provides more information about the estimate, such as precision, making them easier to compare and interpret. There are three main types of intervals that are commonly calculated. They are tolerance intervals, the bounds or coverage of a proportion of the distribution with a specific level of confidence. Next, we have confidence intervals, the bounds of the estimates of a population parameter. Thirdly, we have prediction intervals, the bounds of a single observation. A tolerance interval may be used to set expectations on observations in a population or help identify outliers. A confidence interval can be used to interpret the range for a mean of a data sample that can become more precise as the sample is increased. A prediction interval can be used to provide a range for a prediction or forecast from a model. For example, when presenting the mean estimated skill of a model, a confidence interval can be used to provide the bounds on the precision of the estimate. This can also be combined with p-values if the models are being compared. Hello and welcome back. A tolerance interval defines the upper and lower bounds within which a certain percent of the process output falls with a stated confidence. A statistical tolerance interval contains a specified portion of the units from the sampled population or process. The interval is limited by the sampling error and by the variance of the population distribution. Given the law of large numbers, as the sample size is increased, the probabilities will better match the underlying population distribution. The example on screen is an example of a stated tolerance interval. The range from X to Y covers 95% of the data with a confidence of 99%. You refer to these intervals as statistical tolerance intervals to differentiate them from tolerance intervals in engineering that describe the limits of acceptability. The illustration on screen helps you to visualize the difference between a confidence interval and a tolerance interval. A tolerance interval is defined in two terms of quantities. Number one, coverage, the proportion of the population covered by the interval, and number two, confidence, the probabilistic confidence that the interval covers the portion of the population. The size of the tolerance interval is proportional to the size of the data sampled from the population and the variance of that population. There are two main methods for calculating tolerance intervals depending on the distribution of data, and they are parametric and non-parametric methods. All right, let's define those two. So what is a parametric tolerance interval? It uses knowledge of the population distribution and specifying both the coverage and the confidence, often used to refer to a Gaussian distribution. All right, the second is a non-parametric tolerance interval. Use rank statistics to estimate the coverage and the confidence, often resulting with less precision, wider intervals, given the lack of information about their distribution. Tolerance intervals are relatively straightforward to calculate for a sample of independent observations drawn from a Gaussian distribution, which is good because most of our data will fall into that distribution. Hello, welcome back. In this lesson, let's work through a demo of calculating the tolerance intervals on a data sample. First, let's define a data sample. You're going to create a sample of 100 observations drawn from a Gaussian distribution with a mean of 50 and a standard deviation of 5. During the example, you're going to assume that you are aware of the true population mean and the standard deviation, and that these values must be estimated. Because the population parameters have to be estimated, there's an additional uncertainty. For example, for 95% coverage, we could use 1.96 or 2 standard deviations from the estimated mean as the tolerance interval. You must estimate the mean and the standard deviation from the sample and take this uncertainty into account. Therefore, the calculation of the interval is slightly more complex. Next, you must select a number of degrees of freedom. This will be used in the calculation of the critical values and in the calculation of the interval. Specifically, it's going to be used in the calculation of the standard deviation. Remember that degrees of freedom are the number of values in a calculation that can vary. Here, we have 100 observations. Therefore, we have 100 degrees of freedom. You don't know the standard deviation, therefore it must be estimated using the mean. This means our degrees of freedom will be n-1, or 99. Next, you're going to specify the proportional coverage of the data. In this example, you're interested in the middle 95% of the data. The proportion is 95. You must shift this proportion so that it covers the middle 95%. That is, from the 2.5th percentile to the 97.5 percentile. You know that the critical value for 95% is 1.96, given that we use it so often. Nevertheless, you can calculate it directly in Python, given the percentage 2.5% of the inverse survival function. Next, you'll need to calculate the confidence interval of the coverage. You can do this by retrieving the critical value from the chi-squared distribution for a given number of degrees of freedom and the desired probability. You can use the chi2 squared ISF SciPy function to do this. You now have all the pieces to calculate the Gaussian tolerance interval. The calculation in our example is, with DOF is the number of degrees of freedom. N is the size of the data sample. Gauss critical is the critical value, such as 1.96 for 95% of the coverage of the population. And chi-critical is the chi-squared critical value for the desired confidence in degrees of freedom. Running the example calculates and prints the relevant critical values for a Gaussian and chi-squared distribution. A confidence interval is a bounds on the estimate of a population variable. It is the interval statistic used to quantify the uncertainty on an estimate. A confidence interval is different from a tolerance interval that describes the bounds of data sampled from the distribution. It is also different from a prediction interval that describes the bounds of a single observation. Instead, the confidence interval provides bounds on a population parameter, such as mean, standard deviation, or similar. In applied machine learning, you may wish to use confidence intervals in the presentation of the skill of a predictive model. The graphic on screen helps visualize the various levels. The value of a confidence interval is the ability to quantify the uncertainty of an estimate. It provides both a lower and an upper bound and a likelihood. Taken as a radius measure alone, the confidence interval is often referred to as the margin of error and may be used to graphically depict the uncertainty of an estimate on graphs through the use of error bars. For example, suppose all the possible samples were selected from the same population, and the confidence interval was computed for each sample. A 95% level implies that 95% of the confidence intervals will include the true population parameter. 5% of those intervals will not contain that parameter. Often, the larger the sample from which the estimate was drawn, the more precise the estimate, and the smaller, the better the confidence interval. Smaller confidence intervals equals a more precise estimate. Larger confidence intervals, a less precise estimate. Classification problems are those where a label or class outcome variable is predicted given some input data. It is common to use classification accuracy, or classification error, the inverse of accuracy, to describe the skill of a classification predictive model. For example, a model that makes correct predictions of the class outcome variable 75% of the time has a classification accuracy of 75%, calculated using the code on screen. This accuracy can be calculated based on a holdout dataset not seen by the model during training, such as a validation or test dataset. Classification accuracy, or classification error, is a proportion or a ratio. It describes the proportion of the correct or incorrect predictions made by the model. Each prediction is a binary decision that can be correct or incorrect. Thankfully, with a large sample size, around more than 30, you can approximate this distribution with the Gaussian. You can use the assumption of a Gaussian distribution of the proportion, i.e. the classification accuracy or the error, to easily calculate the confidence interval. In the case of classification error, the radius of interval can be calculated using the code on screen. In the case of classification accuracy, the radius of the interval can be calculated using the code on screen. Where interval is the radius of the confidence interval, error and accuracy are classification error and the classification accuracy respectively. N is the size of the sample, square root is the square root function, and z is the number of standard deviations from a Gaussian distribution. Technically, this is called a binomial proportion confidence interval. Commonly used numbers for standard deviations from a Gaussian distribution and their corresponding significance levels are presented on screen. Consider a model with an error of 20%, or 0.2. Error equals 0.2. On a validation dataset with 50 samples, n equals 50. You can calculate the 95% confidence interval, where z equals 1.96. Running the example, you calculated the results of the confidence interval calculated out. You can then make these claims. The classification error of the model is 20%, plus or minus 11%. The true classification error of the model is likely between 9% and 31%. You can see the impact that the sample size has on the precision of the estimate in terms of the radius of the confidence interval. Running the example shows that the confidence interval drops to about 7%, increasing the precision of the estimate of the model skill. Remember that confidence interval is a likelihood over a range. The true model skill may lie outside of that range. By default, it makes Gaussian assumptions for binomial distributions, although other more sophisticated variations on the calculation are supported. The function takes account of the successes, or failures, the total number of trials, and the significance level as arguments and returns the lower and upper bound of the confidence interval. The example demonstrates this function in a hypothetical case where the model made 88 correct predictions out of a dataset with 100 instances, and you were interested in the 95% confidence interval, provided to the function as a significance of 0.05. Running the example prints the lower and upper bounds on the model's classification accuracy. Hello and welcome back. Often you don't know the distribution for a chosen performance measure. Alternatively, you may know the analytical way to calculate such confidence intervals for a score. In these cases, the bootstrap resampling method can be used as a non-parametric method for calculating confidence intervals, nominally called the bootstrap confidence intervals. The bootstrap is a simulated Monte Carlo method where samples are drawn from a fixed finite dataset with replacement and a parameter is estimated on each sample. This procedure leads to a robust estimate of the true population parameters via sampling. You can demonstrate this with the pseudocode on screen. Do keep in mind this is pseudocode. This is an executable code. The procedure can be used to estimate the skill of a predictive model by fitting the model on each sample and evaluating the skill of the model on those samples not included in the sample. The mean or median skill of a model can be presented as an estimate of the model's skill when evaluated on unseen data. Confidence intervals can be added to this estimate by selecting observations from the sample of skill scores at specific percentiles. Recall that a percentile is an observation value drawn from the sorted sample where a percentage of the observations in the sample fall. For example, the 70th percentile of samples indicate that 70% of the samples fall below that value. The 50th percentile is the median or middle of that distribution. The first thing you must do is choose a significance level for the confidence level, such as 95%, represented as 5%, for example, 100 to 95. Because the confidence interval is symmetric around the mean, you must choose observations in the 2.5 percentile and the 97.5 percentile to give a full range. All right, let's take a look at an example. Let's assume that you have a data set with 1,000 observations of values between 0.5 and 1, drawn from a uniform distribution. You're going to perform the bootstrap procedure 100 times and draw samples of 1,000 observations from the data set with replacement. You're going to estimate the mean of the population as a statistic, and then you're going to calculate on the bootstrap samples. This could just as easily be model evaluation. Once you have the sample of that bootstrap statistic, you can then calculate central tendency. In our example, you're going to use the median, or 50 percentile, as we do not assume any distribution. You can then calculate the confidence interval as the middle 95% of observed statistical values centered around the median. First, the desired lower percentile is calculated based on the chosen confidence interval. Then, the observations at this percentile are retrieved from the sample of bootstrap statistics. You do the same thing for the upper boundary of the confidence interval. When you execute the final example, it summarizes the distribution of the bootstrap sample statistics, including the 2.5th, 50th, the median, and 97.5 percentile. You can then use these observations to make a claim about the sample distribution, such as, there is a 95% likelihood that the range 0.741 to 0.757 covers the true statistic mean. Hello and welcome back. A prediction interval is an estimate of the interval in which the future observation will fail. with a certain confidence level, given observations that were already observed. It provides a probabilistic upper and lower bounds on the estimate of an outcome variable. Prediction intervals are most commonly used when making predictions or forecasts with regression models, where uncertainty is being predicted. An example of the presentation of a prediction interval might be, given a prediction y, given x, there's a 95% likelihood that the range a and b covers the true outcome. The prediction interval surrounds the prediction made by the model and hopefully covers the range of true outcomes. The diagram on screen helps to visually understand the relationship between prediction, prediction interval, and outcome interval. A prediction interval is different than a confidence interval. A confidence interval quantifies the uncertainty on an estimated population variable, such as the mean or standard deviation, whereas a prediction interval quantifies the uncertainty of a single observation estimated from a population. In predictive modeling, a confidence interval can be used to quantify the uncertainty of an estimated skill of a model, whereas a prediction interval can be used to quantify the uncertainty of a single forecast. Prediction intervals will almost always be wider than confidence intervals because they account for the uncertainty associated with error. Hello and welcome back. A prediction interval is an estimate of the interval in which the future observation will fail, with a certain confidence level, given observations that were already observed. It provides a probabilistic upper and lower bounds on the estimate of an outcome variable. Prediction intervals are most commonly used when making predictions or forecasts with regression models, where uncertainty is being predicted. An example of the presentation of a prediction interval might be, given a prediction y, given x, there's a 95% likelihood that the range a and b covers the true outcome. The prediction interval surrounds the prediction made by the model and hopefully covers the range of true outcomes. The diagram on screen helps to visually understand the relationship between prediction, prediction interval, and outcome interval. A prediction interval is different than a confidence interval. A confidence interval quantifies the uncertainty on an estimated population variable, such as the mean or standard deviation, whereas a prediction interval quantifies the uncertainty of a single observation estimated from a population. In predictive modeling, a confidence interval can be used to quantify the uncertainty of an estimated skill of a model, whereas a prediction interval can be used to quantify the uncertainty of a single forecast. Prediction intervals will almost always be wider than confidence intervals because they account for the uncertainty associated with error. Hello and welcome back. Let's make the case for linear regression prediction intervals with an example. First, let's define a simple two-variable data set where the output variable, y, depends on the input variable, x, with some Gaussian noise. Running the example prints the mean and the standard deviations of the two variables. We can also create a plot for it. You can see that there's a clear linear relationship between the variables, with the spread of the points highlighting the noise or random error in the relationship. Next, let's develop a simple linear regression that, given the input variable x, will predict the y variable. You can use the linear regression function to fit the model and return the b0 and the b1 coefficients of the model. You can then use those coefficients to calculate the predicted y variables, called y hat, for each of the input variables. The resulting points will form a line that represents the learned relationship. Running example fits and prints the coefficients. The coefficients are then used as inputs from the dataset to make predictions. The resulting inputs and predicted y values are plotted as a line on top of the scatter plot for the dataset. You can clearly see the model has learned the underlying relationship in the dataset. Now let's go ahead and make a prediction with our simple linear regression model and add a prediction interval. We fit the model as before. This time you'll take out one sample from the dataset to demonstrate the prediction interval. You're going to use the input to make the prediction, calculate the prediction interval for the prediction, and then compare the prediction and interval to the known expected values. In our code, you can see we've defined the input, prediction, and expected values. Next, you can estimate the standard deviation in the prediction direction. Next, you can calculate this directly using NumPy arrays as follows. Next, you can calculate the prediction interval for a chosen input. You're going to use a significance level of 95%, which is 1.96 standard deviations. Once the interval is calculated, you can summarize the bounds of the prediction to the user. Running the example estimates y hat standard deviations and then calculates the confidence interval. Once calculated, the prediction interval is presented to the user for the given input variable. Because this is a contrived example, you know the true outcome, which you can also display. You can see that in this case, the 95% prediction interval does not cover the true expected value. A plot is also created showing the raw data set as a scatter plot. the predictions for the dataset as a red line, and the prediction interval as a black dot and line respectively.